In this lecture, we're going to finish this table. Previously we looked at the two situations in which order matters with and without replacement. So order matters with replacement. We had n choose n to the power r. We didn't have any specific name for that. And then we looked at permutations. I'm going to choose things. The order in which I choose them matters, and I have n choices initially. I make choices without replacement, and I'm ultimately going to make r choices. There were this many ways to do that. What if I'm choosing things like that, but the order in which I choose things doesn't matter? Then we had n choose r, which was over here, and now we're going to do order doesn't matter, and I'm choosing with replacement. There's only one example that I'm really aware of with this, and this is placing balls in bins, so I'm going to keep saying balls in bins. This one is, I think, the most difficult of these to figure out. It's also the least useful because, say, if you want to use this counting in probability, for example, then if you have a bunch of equally likely events, then the probability of some event is just count the total number of outcomes and then count the number of outcomes in the event of interest. So you could say, if I want to know how many poker hands involve three of a kind, I can count how many poker hands there are, count how many of those are three of a kind, and then just divide how many are three of a kind divided by the total number of hands, and that'll give me the probability of getting a three of a kind. And so you can use these three things occur in kind of natural scenarios where you're counting probability of equally likely events, and this one doesn't. This is not counting probability of equally likely events. So it's not equally likely. I'm going to just roughly say that because if you try to use this for counting, you're going to get events that are not equally likely because of multiple countings of the same event. And I'll just leave it at that. But our goal for this lecture is to fill in this empty blank here. So let's do a quick example. So I'm going to have indistinguishable balls. So here in this example, I'm going to have three balls, and I can't tell which is which. Okay, so they're not, I don't have like a first and a second and a third, or a red one and a green one and a blue one. It's three balls that I cannot tell apart. And in this example, I'm going to put them in two bins. Okay, so here, maybe I put the first one here, and then the second one here, and then the third one here. And then over here, maybe I'm going to do the first one here, then the second one here, then the third one here. To me, these are indistinguishable outcomes. Okay? So I look at these three balls, I don't know which one was placed first, which one was placed second, and which one was third, because I said they're indistinguishable balls. Right? So if I knew which one was the first one, then order would matter. Here, in the scenario where order doesn't matter, what order I place these things in the bins, because if they end up with two in the first bin and one in the second, I count those as the same outcome. Okay? So I mean, we could just rewind the video and see which one was first or which one was second, but for the sake of, we're describing a scenario in which these two outcomes are indistinguishable from each other, even if the balls weren't placed into the bins in the same order. Okay, so this is the kind of problem we're looking at now. And so we want to count this. So previously we had NPR for permutations and NCR for combinations. Here I'm going to do NGR. The NPR and NCR are standard notations. You'll see those notations elsewhere. This NGR is non-standard, but I'm not really aware of any standard notation for counting this value, so I just gave it the name G. Okay. And let's place this into the context of our kind of bigger problem. We have number of experiments and number of distinguishable outcomes. So here, I can distinguish the bins from each other. There's bin number 1 and bin number 2 and maybe 3 and 4 and 5. The balls themselves are indistinguishable. I don't know which one was the first or which one was the second, etc. Each experiment is going to be placing one ball in a bin. Okay? The number of outcomes is the number of bins. Right? So let's say I have three balls and I have bin A and bin B and bin C. So the first experiment will be I'm going to take a ball, put it in one of the bins. If I put it in bin B, then the outcome of the first experiment was B. Okay? Take the second ball and put it in bin A, then the outcome of the second experiment was A. Right? So here the experimental unit that we're talking about is the placement of an individual ball, and the outcomes are the bins that I could place that ball into. Okay? So instead of thinking about balls and bins, I'm going to think about balls and dividers. Okay? So if I have n bins, I can take space and separate it into n bins by placing down n minus 1 dividers. Right? So if I want to separate space into 3 bins, I'm going to put down a divider between 1 and 2 and a second divider between 2 and 3. So with 2 dividers, I've created 3 separate regions, right? 3 separate bins here. Okay. So actually, it turns out there's a pretty nice way to solve this problem, right? Is I have R balls, right? Each ball is an experiment. We're doing R experiments. That means there are R balls. Indistinguishable outcomes means in bins, which means n minus 1 dividers between bins, right? So let's say I'm in this scenario where I have 3 bins and 4 balls. So 3 bins means 2 dividers. Okay? 2 dividers between 3 bins. And I'm going to have 4 balls. So what I'm going to do is say number of balls, which is R, plus the number of dividers, which is n minus 1. So here the number of dividers is 2 and the number of balls is 4. So I'm going to make 6 slots. 2 of them are going to be for dividers and the other 4 will be for balls. All right, so now I'm just going to choose 2 slots for dividers. How many ways are there for me to choose 2 slots for dividers? Well, there's 6 slots. Choose 2 for dividers. That's 6, choose 2. We know what that is. Okay, so I'm going to pick that one and that one. Okay, those are my 2 slots where I put dividers. And now everywhere else, I put a ball. And to me, this is going to say, okay, here, this is everything to the left of the first divider is bin 1. Between these dividers is bin 2. To the right of this divider is bin 3. So I'm going to look at bin 1 and 2 and 3. And what I did is I have 1 ball here in bin 1, 1 ball here in bin 2, 2 balls here in bin 3. So take 6 places, 4 of them for balls, the other 2 for dividers. Choose which 2 places to put the dividers, and then everywhere else gets a ball, and that corresponds to an outcome. And all the different ways I could do that gives me all the different outcomes. So, well, let's write it down. What we said is we're going to have R plus n minus 1. That is the number of slots that we draw. Okay. R of them are going to be occupied by balls. The other n minus 1 will be occupied by dividers. And I choose n minus 1 of them to put the dividers. And then the other R will get balls. And this is it. That's it. That's our answer. This is the number of outcomes. Okay. Just frame it in the way of balls plus dividers. I choose where to put the dividers. Everywhere else gets a ball. So note that this is also equal to, and you can see that this is equal in a couple of different ways. So if this number choose n minus 1 is the same as this number choose R. The reason, well, if you write down what this is in terms of factorials, you can see it's easy. It's going to be R plus n minus 1 factorial in the numerator, and then n minus 1 factorial and R factorial in the denominator. Or you could just see, well, I could choose the n minus 1 places to put the dividers and then everywhere else gets a ball, or I could choose R places to put the balls and everywhere else gets a divider. And there's the equal number of ways to do that. Once I choose where to put everything of one type, everything of the other type goes in the remaining places. So either one of these works as a number of ways to count the different outcomes for balls and bins. Right? Let's go back. So here, I've kind of written out all the possible examples. So I have 3 bins and 3 balls. 3 bins means 2 dividers. So I'm going to do 3 bins plus 2 dividers is 5. And I'm going to choose 2 places to put dividers. So I have 5 choose 2, which I compute over here is 10. 5 choose 2 is 10. So I wrote down, I have 5 slots. Each of these sets of 5 slots is going to get 2 dividers. And then the other 3 places will be for balls. So I've written down all the possible ways to do that. Okay. So now let's look at the first one. I put slots in these places, and the other places are going to get bins. So this would correspond to bin 1 is empty. So if we look to the left of the first divider is bin 1, there are no balls there. Bin 2 is also empty. Right? So I look between divider number 1 and divider number 2. That's where bin 2 is, and there's nothing there. And then bin 3 has all 3 balls in it. Okay, so this set of slots would correspond to this kind of outcome. So over here, this one, well, there's bin 1, there's bin 2, there's bin 3, so that would correspond to this. So, and you can go in and fill out the rest for yourselves. You can see how kind of this picture, I think, makes a little more sense than this one. But thinking about it as R plus n minus 1 slots, and I choose which of the slots to put the dividers in, I think makes it easier to understand why this this answer is the correct one. So you can fill in the rest of these for yourselves, kind of translate between the not easily interpretable picture and the easily interpretable picture, and convince yourself that that's the correct number. So this relates back to Pascal's triangle. So what I want to do is take Pascal's triangle. So 1, 1, 1, 1, 2, 1. So the sides of Pascal's triangle, those are all ones, and then everything else is the sum of the two numbers above it. So how do we get from here to something that's useful for counting balls and bins? I want to take this first kind of a diagonal of ones and straighten it out so that it becomes my top row, and then take the second diagonal, make it my second row, take the third diagonal, make it my third row, and then I have N and R. So N and R. And this big rectangle should go on infinitely in both directions. Okay. Now, these things are counting balls and bins. Right? So if I look at, say, I need to be careful because this is starting at 0 in some places. Right? So we're going to have 0 balls would be one outcome. Just put 0 balls, right? You can't put them anywhere. And then 1 bin is always 1. I put all of the balls in 1 bin. Right? So R here starts at 0. N here starts at 1. Okay, so we have to be careful of that. But then once we know that this starts at R equals 0, and then R equals 1, R equals 2, R equals 3, N equals 1, N equals 2, N equals 3, etc. Then we can just look very quickly on the table to figure out how many ways to put R balls in N bins. So just taking Pascal's triangle and de-diagonalized it. Right? So we'll look up here and see 1 GR, which is the number of ways to put R balls in 1 bin. There's only one way to do that. Okay? For R equals 0, 1, 2, so I can have 0 balls or 1 or 2 or 3. How many ways are there to put those balls into 1 bin? There's only one way to do that. Put all of them in the 1 bin that's there. Right? So 1 GR equals 1 for any R. Okay? And now N plus 1 GR means I want to put R balls in N plus 1 bins. There are this many ways to do it. Right? So this is a recursive formula here. So I'm defining N plus 1 GR in terms of N G other things. So here the N plus 1 bin scenario is reduced to something that's in terms of the N bin scenario. Why is this equal to this? Well, so let's say I have N plus 1 bins. So I go to the last bin and I can put 0 balls in it. And in that case, I have to put all R of the balls in the previous N bin, right? So if I don't put any balls in the N plus first bin, then I have to put all R of them in these bins, and there are this many ways to do that. Okay. Or I could put 1 ball in the last bin, and then I have R minus 1 balls to put in the previous bins, so there are this many ways to do that. I could put 2 balls in the last bin, and then I have to put the other R minus 2 in the previous N bins, all the way down to, I could put all R bins, or all R balls in the last bin, and then there are this many ways for me to put the remaining 0 balls in the previous N. So I'm going to say, break this down to choosing in stages. The first stage is I choose how many balls I'm going to put in the last bin. And I could do 0, 1, 2, 3, etc. And after I do that, I want to know, okay, how many ways are there for me to distribute the remaining balls in the previous N bins? Okay. So if I put 0 balls in the last bin, there are this many ways for me to put the remaining R balls in the other bins. So the first row is this number, the second row is this number, the third row, if I had written it instead of putting ... would be the third number, all the way down to the last row is this number. So that's where this recursion comes from, is I want to think about placing balls into N plus 1 bins, and I want to break it down into 2 choices, determining how many balls I'm going to put in that last bin, and then after I put that many in the last bin, how many ways are there to distribute the remaining balls in the previous N. Okay, and I arrive at this recursion. So now this recursion is pretty nice. We get something called the hockey stick identity, which is, has this formula. Right? So this row here is the same as this. Okay, so we've already claimed that NGR is equal to this value, which is the same as this value. And so this says that n plus 1 gr, which is this, is equal to the sum of ngr, ngr minus 1, ngr minus 2, all the way down to ng0, which is what these values are. And the highlighted part, those are it's the sum of ngk as k goes from 0 up to r. Okay, so this row here is in symbols the same thing as this one is in actual values. Okay. And it amounts to saying that if I take one of the diagonals of Pascal's triangle and add down a diagonal, the sum is just the thing that's, if I'm adding down a diagonal that's going to the right, the sum is just the thing that's here to the left. So 1 plus 2 plus 3 plus 4 is 10. So if I go over here, 1 plus 4 is 5. And this is the hockey stick identity. Alternatively, it tells me that if I take Pascal's triangle and rewrite it like this, if I want to know what should go in one slot, I add up all of the things. Say I go up one and then add everything to the left. And that's what this is telling me. So why is this true? Why is this hockey stick identity true? You could actually do a proof by induction of this, but it's not quite easy. So I'm going to fake a proof. I'm going to fake a proof by induction. And I'm going to say, well, if I just pick this diagonal here, I'm going to claim that if I add things down the diagonal, then the sum will be whatever is down and to the left on the next row. And the fake proof by induction is going to be, well, I know that this thing is this thing plus this thing. Okay. My proof by induction is going to say, well, let's assume I already know that if I add this up, I'm going to get this part. Okay, so if I add this and this and this, I'm going to get that. If I add this and this and this and this, right, these four things, well, I know the first three is just going to give me that, plus this other one is going to give me that. Right, so kind of this picture, knowing that these two things is how I got that. This picture says, well, if I add down a diagonal here, and I want to know that it's equal to that, well, I can say back up one, if that's equal to that, plus this one additional term gives me that. Right? So there's a fake almost proof by picture of the hockey stick identity. Right? So now we've finished our table here. We know how to count all of these things, and well, we'd like to practice. So a big important part of this would be reading a problem and figuring out which of these four boxes am I in. In this scenario, does order matter? Does it not matter? Am I doing with replacement? Am I not doing replacement? And then after that, you just plug in N and R.